Here we go. Question 2.26a. So we're starting it with aniline, and we want to make this compound where we have an isopropyl group and we have a nitrile that are para to one another. Well, we know that we can make the nitrile by Sandmeyer chemistry because we have this amine here. So we also know that an amine is an orthopara directing group, right? So we could put in the isopropyl group here, and you might think, well, I could just go ahead and install that using, isopropyl chloride and iron 3 chloride, but unfortunately that will not work because we know that Lewis acids are incompatible with the amine. It's going to complex with the Lewis acid, makes the ring really deactivated, so that won't work. So we're going to scratch all that. And so what we're going to have to do is we're going to have to acetylate, we're going to have to acetylate the amine like this. Okay, so let's acetylate that amine. And what that will do is that'll mitigate the reactivity such that the nitrogen will not react with the Lewis acid. So now we're free to install that isopropyl group. We'll use isopropyl chloride. So this is just a Friedel-Crafts alkylation. We'll use iron 3 chloride. And there you go. Now we've got our isopropyl group installed on our ring. We've still got our acyl group. So we'll draw that out here. Okay. Now, in order for us to use Sandmeyer chemistry, which is a great idea, right? We would just think, well, as long as I have the diazonium ion, this guy, okay, all I have to do is Sandmeyer chemistry. Just use copper 1 cyanide, and that will install the nitrile. But in order to make the diazonium ion, we're going to have to convert this to the amine, and then we're going to have to do a diazotization. And we saw that we can hydrolyze this using sodium hydroxide. It's a slow reaction, but it will work. So we'll just put sodium hydroxide, and then we're going to hydrolyze the acyl group to produce our aniline like this. And now we've got our isopropyl group here. So what do we need to do next? We need to diazotize. And for that, we need to use sodium nitrite and HCl in situ. And that's going to make the diazonium ion like this. So there's my diazonium ion. And then the last step is to use Sandmeyer chemistry, to use copper 1 cyanide in order to install my nitrile on my aromatic ring. So there's the synthesis. It's quite a few steps. But as long as you recognize the Sandmeyer chemistry that you'd have to use right away to install that nitrile, you know that you're going to have the amine. You know you've got to do a diazotization. So there you go. And you need to know a little bit about electrophilic aromatic substitution, don't you? Because you've got to know that this is an orthopara director, but it won't work to do a Friedel-Crafts alkylation directly. You first got to do the acetylation, and we talked about that at length in this chapter. Question 22.26e. It's kind of a funny one. We're starting out with benzene, and we want to put a chloro and a fluoro on our aromatic ring, and we want them to be para to one another. Well, we don't have too many ways of installing a fluorine on an aromatic ring, do we? Okay, so for this one, again, we're going to think in terms of our diazonium ion, right? And we know that if we have the diazonium ion, okay, and if we have the chlorine here, all we have to do is treat that with HBF4, hydrofluoroboric acid, and that was the CHEM reaction. So we could pencil that in here. This is the CHEM reaction. Okay, so the CHEM reaction is going to put that fluorine in the position where we want it. So then the question becomes, well, how would I make this compound? Well, diazonium salts always come from a nitro, right, or an aniline derivative. So we've got to have this at some point, right? And then where are we going to get that? Well, we're going to get that from the nitro. So we've got to make the nitro. And luckily, a chlorine is an orthopara director to put our nitro group in. So we can just start with benzene, and we can start by just chlorinating it. So we're going to treat it with chlorine, and I'll use aluminum trichloride as my Lewis acid. So that installs my chlorine on my aromatic ring. Again, chlorine is weakly deactivating, but it's an orthopara director. It's one of the exceptions. And so to install the nitro group, all I'm going to do is treat this with nitric acid and sulfuric acid mixed together, H2SO4. That makes the nitronium ion, not the nitrosonium, but the nitronium ion. You form the sigma complex, you restore the aromatic ring, and you would end up putting the nitro group in the least hindered position, the para position, like that. Now we need to reduce that, same old conditions as always. So first we're going to treat it with a metal like iron, aqueous acid. We'll heat that up. Then you've got to treat that with base like sodium hydroxide, because you'd actually end up with the aniline, right? You'd end up with this, and that's not useful. So you have to deprotonate that. But that gives us our aniline derivative. So now we've got parachloroaniline. So there's my NH2. There's my chlorine. And then we need to diazotize. So we're going to treat that with sodium nitrite and HCl in situ. That's going to give us the diazonium ion. So let's draw that out, N2 plus. We've got our chlorine here. And then again, we just use the CHEM reaction, HBF4, like that. So kind of a lengthy synthesis to make a very simple compound. You know, we're just installing this chlorine and this fluorine, but you can see it's a total of what? 1, 2, 3, 4, 5, 6 steps to get there. And again, you know, what's the clue that you've got to use the, that you got to use the CHEM reaction, because we don't have too many ways of installing a fluorine on an aromatic ring. And so the CHEM reaction is what we would use here. I just want to show you F quickly. I don't think I would bring this one up on a quiz. I mean, I think this would be a good question for a final exam maybe, but for a quiz, it's kind of surprising you with a reaction that we didn't look at a lot in chapter 18, which is addition elimination. Okay, in benzyne intermediates, right? We didn't talk about that a ton. We did discuss it for sure, and I asked you some questions about that on the quiz, but this one is tough without doing addition elimination, because you can think of this coming from aniline, right? And all you would have to do is diazotize it and then treat it with copper 1 bromide. Okay, well, that's well and good. But how do I get from here to here? And the thing is, we do know a way to get there immediately. And that is to just treat it with a strong base like sodium amide, which is going to abstract a proton. Then amide comes in as a nucleophile. So this is an elimination addition. Elimination addition reaction. Okay, so again, this is covered in chapter 18, I believe. It's towards the end of the chapter, and that's where we saw the benzyne intermediate, benzyne. So you can go back and take a look at that, but that's how this mechanism works, and you actually just convert the chlorine to the amine to make aniline like this. Then you diazotize, so you would treat it with sodium nitrite and HCl. You make the diazonium ion. I'm going to draw it out as the salt this time. I'll draw the whole thing just to practice. So there's my diazonium salt. And then you would simply treat that with copper 1 bromide. And of course, this is one of the Sandmeyer reactions. All right. Again, I don't think I'd, try to regurgitate this one on a quiz. Again, I think it'd be good for a final to bring it up as a question. But in a synthesis on the quiz, it would be pretty surprising, because it's something that we didn't look at, a ton. We didn't look at it, all day or anything. Let's try 22.54. So let me find it here in my textbook. So 22.54a is another one I wanted to take a peek at. And 22.54b, these are just more questions where you're asked to propose a synthesis. So 22.54, start with A. So we're starting with benzene. Gotta love a synthesis where you just start with benzene, such a cheap molecule. And then you end up with this. So you're making a tertiary amide, right? So, I think retrosynthesis is really the way to go here. In terms of my retrosynthesis, I mean, I have an acyl group on here. So I just think, okay, well, what if I had this compound? If I had this where I have my nitrogen here, and then I had a hydrogen here, right? I could just treat that with acetyl chloride, okay? And that will do the acylation. But then it's like, well, how do I make a secondary amine? How do I do that? Well, I could make that from a primary amine, and I could do a reductive amination. That would work, right? So then I think, okay, well, what would my primary amine look like? I could start with this primary amine, like this, and then all I'd have to do is treat it with a catalytic amount of acid, sodium cyanoborohydride, so sodium cyanoborohydride, and then in this case you'd use formaldehyde. Okay, well then the question becomes, okay, well how do I get from here to here? How do I make this compound? Well, you can see that there's only a carbon and a nitrogen. So if I could take this, and if I could make the nitrile, benzonitrile, then I can reduce that using lithium aluminum hydride, right? That's all I've got to do. Well, how do I make the nitrile? I make it using Sandmeyer chemistry, right? So what would I do first? First, I would install the nitro. So we'll treat this with nitric acid and sulfuric acid. So let me write that down. Nitric acid, sulfuric acid. That's going to install our nitro group. So I'll write it up here like this. Then I want to reduce that. So I'll treat it with iron and aqueous acid, followed by sodium hydroxide. That just makes aniline. So now all I've done is made aniline from benzene. Now I want to diazotize, so I'll treat this with sodium nitrite and HCl, and that will give me the diazonium ion. Let's see, like this. There we go. Now I want to convert it to the nitrile. So I'm just going to treat it with copper cyanide. That gives me, oh, I'm going to run into space here, aren't I? So look, let me keep going this way. I'll keep going down here. So we're going to treat this. Why don't we make kind of a funky arrow here? Go like this. Okay, so I'm going to treat this with copper cyanide, and that's going to give me this compound, benzonitrile. Then I can reduce that using lithium aluminum hydride, but you always have to follow up by treatment with water. And that's going to give me that primary amine that I wanted. So now that I've got the primary amine, I can convert it to the secondary amine using a catalytic amount of acid, formaldehyde, right, because I only need one carbon, and sodium cyanoborohydride. So that gives me this compound. I'm really running out of space here, aren't I? There we go. So now I've got my methyl group here. And then the last step is going to be to install the acetyl group. So I just treat it with acetyl chloride, like that, and that is going to put my acetyl group on there. So I'm going to end up with this. I'll draw my methyl group pointing down like they do in the book. And there you go. There's your product. So, I mean, how many steps is this total? Let's count. I'll use the green pen. We've got 1, 2, 3, 4, 5, 6, 7, 8. Wow. 9-step synthesis in order to make that compound. So not a simple synthesis, that's for sure. Okay, a lot of steps. But again, you just would want to solve this using retrosynthesis, and that's what this is here. If you're not sure how to go forward, always start by going backwards then, right? And that will usually, help you discover, what the best method of attack would be to make the molecule in question. Let's try 22.54b. So this is 22.54b. And we're starting it with benzene again. And we want to install a cyclohexyl group. So I'm thinking Friedel-Crafts. And then you also want to have the carboxyl group here, COOH, so the carboxylic acid. I mean, with this one, I'm just thinking we would install the cyclohexyl group first using Friedel-Crafts chemistry, and then we could just do a diazotization, or we could use Grignard chemistry. Either way is going to work, right? So we would treat this with cyclohexyl chloride, aluminum chloride. This is a Friedel-Crafts calculation. We would end up with this compound. So where we have our cyclohexyl here. So if we wanted to go the Greenyard route, we would just treat this with bromine and the Lewis acid, iron 3 bromide. That would install the bromine para, this big old cyclohexyl, like this. Then we would treat this with magnesium in diethyl ether. So I'll just write my diethyl ether like this. This will give me my Greenyard reagent. So I'm going into a lot of detail here, probably more detail than the book does, but then you have your MGBR. Then what you would do is you would treat that with carbon dioxide in the next step. And then in the last step, you just treat it with acid. And that's going to give you the carboxylic acid. If you want to go the Sandmeyer route, that would work too. I don't see why not. You could just do the nitration on the ring. So since this is an ortho para director, you would just treat this with nitric acid and sulfuric acid. There we go. And that would install the nitro group. So let's draw a nitro group over here. Then you're going to reduce that using iron and aqueous acid, followed by treatment with sodium hydroxide. Again, that's going to put the amine here, which will be primed for diazotization to install the nitrile. So first we're going to treat this with sodium nitrite and HCl. That's going to make the diazonium ion. So let's draw out the diazonium ion. There we go. Then we're going to treat that with copper 1 cyanide. So I'll do both steps here. So copper 1 cyanide, that replaces this with the nitrile. And then in the last step, you just hydrolyze it with acid. And that hydrolyzes it to the carboxylic acid. And then you've got the desired compound where you have your carboxyl group up here, and that's it. So again, neither of them are simple, but they both provide an elegant route to the desired compound where you have the cyclohexyl group and the carboxyl group para to each other. Let's try a nomenclature problem, and we'll take a look at 22.40. So this is just practice of nomenclature. Let's see here, 22.40. So we just are given some structures and asked to come up with some names. So the first one is this. We've got 2 methyl groups here and 2 methyl groups here. Remember, whenever you're naming an amine, you can always think about naming it like an alcohol. So we have the longest carbon chain, and it's got to contain the functional group, which is the amino group. So if you had a 1-hexanol, this becomes a 1-hexane amine, right? We replace all with amine. So this is some kind of 1-hexane amine. And then you can see what the rest is. We have 2,2,3,3 tetramethyl. So this becomes 2,2,3,3 tetramethyl 1-hexanamine. And that is it, my friends. Remember to separate letters and numbers with hyphens. The next one is a ketone because it's got 2 functional groups in the molecule, and we discussed this in the first lecture on chapter 22. Whenever you have a functional group that has an oxygen in it, that is the one that takes precedence. And so this compound has an amine and it has a ketone. So this compound is a ketone. So this is some kind of cyclohexanone. This is going to be carbon number 1. This would be 2, 3, and 4. So we've got a 4-amino 2,2-dimethyl cyclohexanone. So we can put all that together. So we've got 4-amino 2,2-dimethyl cyclohexanone. And could anybody tell me what the stereochemistry is at carbon 4? Is it R or S? If I take a look at the chirality center, I've got the lowest priority group going behind the page or behind the screen. That's your hydrogen. It's number 4. The nitrogen is number 1. This is going to be group number 2, and this will be group number 3. So I go from 1 to 2 to 3, which is S, and so this is an S compound. I'll put that in the name, and so the compound is S4-amino 2,2-dimethyl cyclohexanone. Next one, you've got 2 cyclobutyl groups on it, so let's write that down. We've got our amine with a methyl. We've got a cyclobutyl group here, and then we have another cyclobutyl group there. So we could call this dicyclobutyl methylamine. That would work because we've got 2 cyclobutyl groups. And remember, when you've got cyclobutyl, okay, and then you've got dicyclobutyl, remember you ignore prefixes except isocyclo and neo, so C counts, and then you've got methyl, and you alphabetize that according to the letter M. So obviously dicyclo comes first, so we get dicyclobutyl methylamine. So let's write that down. Dicyclobutyl methylamine. The next one is an aniline derivative. We've got the amine on the aromatic ring. We've got 2 methyl groups, one here, and then we have the bromine here. Remember, we want a number to give the lowest possible numbers for our substituents, starting with the first point of difference. So we'll go clockwise, 1, 2, 3, 4, 5, 6. So I've got 3 bromo, and then I've got 2,6-dimethyl. Well, bromo comes first because we ignore the D in dimethyl. So this is 3 bromo, 2,6-dimethyl aniline. So 2,6-dimethyl aniline. Next, the last one, or second to last one, is where we have another aniline derivative. We've got 2 methyl groups on the nitrogen of the aniline derivative, and then we've got a propyl group over here. So this is going to be some kind of NN dimethyl aniline, and we've got a 3 propyl group. So we've got NN dimethyl. That's one group, and then we've got a propyl group. Okay, those are the 2 groups. Well, methyl is going to come before propyl because M comes before P in the alphabet. And so this becomes NN dimethyl propyl aniline. So we'll scribble that down. This is NN dipropyl. No, NN dimethyl. I'm getting tired. NN dimethyl 3, right? Because we have 1, 2, 3, 3 propyl aniline. All right, and then we could try F. I mean, we didn't look at the nomenclature of heterocycles in detail. I told you to skip that section, so I would never ask you this one directly, but I mean, it's still not that difficult to name as long as you know that in 22.40 that this aromatic compound, when you have 2 double bonds like this is called pyrrole. So pyrrole, like that. And so the compound in question is just this, where we have nitrogen in our ring. We've got, here we go, an ethyl group here, an ethyl group here, and a methyl group there. So it's N-methyl. So we've got an N-methyl. And if that's carbon, or if that's the number 1, 2, 3, 5, then we've got 2,5-diethyl. So 2,5-diethyl. So according to alphabetization, you've got methyl and diethyl. Well, ethyl is going to come first, so the compound is 2,5-diethyl and methyl pyrrole. So 2,5-diethyl and methyl pyrrole. And there you have it.